Hello, my name is Yang Li, and our previous lesson video stopped at here. And we have introduced slope of the secant line, and then we can transfer the slope of secant line to the tangent line. So, and then today we're going to use the this example, okay? We're going to use function fx equals square root x at x equals 1. Okay, we use this one. Okay, we use this one to, at this point, we can see that when the graph is here at the beginning, let me just show this one here. At the beginning here, when x equals to 1, this x equals 1, we look at the intervals 1 unit to the right is 2, and 1 unit to the left is 0 here, right? So you can see that this curved line, the gray one, is tangent at the x equals 1 here with the tangent line like this. But you still can see that this line here, they have some gap there, right? You see here? In between the curved line square root x and the straight line x plus 1 over 2, they have some gap there. But now we're thinking about make the interval smaller, means we go x, the interval go this way, closer to 1. So when we look at this graph here right now, this is the one to the left by 0.5 unit lower and 0.5 point higher, right? 0.5 higher. So you will see here, you will see this part of the graph. You see that? You see the gap in between the straight tangent line and the curved line a little bit different now, closer now, right? You see here is more difference here, like this one here. And here is more difference, the more gap there. But here the gap is smaller right now because of the interval. We are narrowed down the interval in between 0.5 to 1.5. That's about center at 1 here. From here to here, only 0.5. From here to here, another 0.5 interval. But here you have one interval. Here you have one interval. See that? Okay, if we do the same thing, continue, you can see that if we do the same thing, continue, and what happens? Here, this one still 1 here, huh? Instead of going through the 0.5 intervals from the left and the right, we can go even closer. Look at this one here. Even closer, like this. And you can see that here only what? 0.25, right? Here also 0.25. And you can see that this time, the curved line, the straight line here almost coincide. Okay, if we do the same thing, even closer about the 1 here, this is the 1, and this one is about like what? 0.05 higher. This one just 0.05 lower. What happens? You can see that this graph and this graph almost the same. And this is the one from this process, we will learn that later on, we're going to study this also. we can use the tangent line to approximate the value of the secant line, or the approximate value of the function, if the value of the x is very, very close to the given point there. Okay, so we can use the tangent line to be a good approximation to find the value of the function if the x is very, very close to the given point there. Okay, but that's later on. We're going to study this part about the differentiation there. Now let's continue. Based on all this, we can get what we can introduce formally right now. We formally introduce the definition of the tangent line like this. Actually, we had this already before, but here we have formally introduced that tangent line to the fx at A is a line passing through this given point, which is A and FA, and then one limits x approach to A, you have the quotient difference here, fx minus fa over x minus A. And of course, as what we mentioned, that you can have the other format starting from the A, you can add by edge. So you're going to have this kind of definition. Okay. So this is based on previous lesson. We can formally define this as a definition of the tangent line in two formats. Of course, from here, later on, we will introduce the slope, the definition of the derivatives at the function at the one point will be the same as this one. So we actually use what? The tangent line slope used as an example to introduce the derivatives. Okay, that's what we're trying to do. Now, to practice more about this one, let's do some of the example here first, okay? Let me explain this example. They said, find the equation of the line tangent to the graph of fx equals x squared at x equals what? 3, right? So what, see here, this is the graph of the fx equals x squared. This is the parabola, right? Now, when we do this one, we can use the definition. We introduce it here. This one, fx minus fa. Here, we're talking about the a is what? 3. So we directly apply that formula. We can get definition of the tangent line. We can directly get this one. Tangent line equals what? The 3 is the a. So x approach to a is 3, fx minus f3 over x minus 3. And fx is x squared. So that's why they plug in x squared here. Minus f3. 3 squared is 9, like this. But be careful, in chapter 1, we learned about limits, right? But if you directly do the limits, x approach 3, you go to here, you go to here. What happens? You will get the limits x approach to 3. You have 3 squared minus 9 over 3 minus 9. You can see that something wrong there. 3 squared is 9. 9 minus 9 is 0, right? 9 minus 9 is 0. And the bottom one is x minus 3 here, right? So you have what? 0 over 0 type. This is called the indeterminate. We cannot solve this one. But fortunately, this function is removable because they're using what? The formula we call that a squared minus b squared equals to a plus b, and a minus b, like this. So here, if you use this one, you can have what? X squared. This is 9, right? Minus 3 squared. You're going to equals to what? X plus 3 and X minus 3. This is called, the formula is called what? This formula is called difference of squares, right? That's what we learned before. So in my lecture here, I'm trying to break it down. So if you forget the formula, you can quickly review this part. And then you understand why they got from here to here. First one go to here is plugged in, and then from here go to here. You will know why you got it from here to here. And if you got this one, it's easy, so you can cancel this 2. And then so you have limits x approach 3, x plus 3 here. 3 plus 3 is 6. So we can find the slope of what? The second, the tangent line now for the function fx equals x squared at the point x equals 3. Okay. Of course, remember we learned about how to find tangent line since we know the slope right now, right? If we knew the slope, the things would be easier here. If we knew the slope here, we knew the slope at x equals 3 here, right? So we can find the tangent line. We can use in the pre-calculus, we'll learn that that's a point. We use a point slope form. Will be easier, okay, at this case. So we go what? Y minus y1 equals the slope and x minus x1 like this. And right now, at this point, we know that this is x equals 3, right? And the y equals 3 squared is 9, like this. So we will have y minus y1, we put as 9, equals slope. Slope, we find it here. We just find slope is 6, huh? 6 and x minus x1. So x1, we just put in as a 3, right? Because we're looking for that point there. And then we can change it to what? See here, that's what they got here. Y minus 9 equals 6 times x minus 3. Of course, this is called the point slope form of the line. And we can simplify this one. We add by 9 on both sides. So we will get y equals 6. So this one times this one, 6x. This one times this one, minus 18 and plus 9. Finally, we got what? Y equals 6x minus 9, which is this one here. And this one we call it as what? Remember, we learned before with the algebra. This one equation with the form we call it slope intercept form. Okay, so the following video will continue with 3.2 example. We're gonna go over detailedly. So when you listen to Ms. Lee's lesson, I'm trying to build up a close relationship between the calculus and the previous math. So you will have no difficulties there when you are reviewing the algebra geometry trick and apply to the specific topics of calculus. That will make the calculus easier, okay? And if you have any questions, please let me know. Thank you. Bye-bye.